Subtopic 1.5 is called atomic spectroscopy. So we're looking at the light and its interaction with atoms. Now, the first little bit here, it's talking about flame tests and atomic absorption spectroscopy are analytical techniques that can be used to identify elements, and these methods rely on electron transfer between atomic energy levels. So the first thing you need to be able to do is you need to be able to write the electron configuration using subshell notation of both atoms and ions for any of the first 38 elements of the periodic table. Now, most of them are pretty straightforward. There are a couple that are a tiny bit tricky, but there's only a few exceptions, so it shouldn't be too tricky. Now, the subshells that you'll need to worry about are these ones here. So you have got 1s all the way up through to 5s, and that's for strontium, which is element number 38. The transition metals, which obviously the ones, the D block in the center sort of portion of the periodic table, that is where things get a tiny bit trickier. But only the first row of that is relevant to this course. So a few of the rules that we think that we talk about do work in other rows in further rows of the periodic table or the transition metals, but we only care about the first one, which does make things a bit simpler. Now, for those transition metals, it says here, or I wrote, by default they have a filled 4s subshell and a partially filled 3d subshell, except when one electron can be taken from the 4s orbital to either half fill or fully fill the 3d orbital. So what I've done here is I've gone into the two exceptions to just gradually filling the subshells bottom to top, and we've got them just here. So chromium has 1s2, 2s2, 2p6, 3s2, 3p6. Now, often it would have been 4s2 and 3d4, but instead you take one and make this 4s1 instead, and 3d5. Now, if you were using the noble gas notation, where you absorb much of the electron configuration into square brackets with the previous noble gas, in this case argon, you would do the exact same thing, and you'd put argon 4s1 3d5. Similarly, copper is the second last transition metal, and if you were filling it normally, you would have 4s2 3d9, but if you can take one electron and take it out of the 4s and the fully filled 4s, dropping it down to 4s1 and put it into the d orbital to make it fully filled, then that is what needs to happen. Now, the actual reason for why that happens is not really important. Suffice it to say that this final configuration, the 4s1 3d5 for chromium and 4s1 3d10 for copper, those are the most energetically stable versions of those elements. Now, before I continue, making it very, very clear, those are the neutral elements. So they are not chromium and copper ions, they are neutral chromium and copper. Now, every other one you should be comfortable with because they just fill these orbitals one by one. Now, when we go to start ionizing, so stripping electrons off of our elements, we have another rule or two. Now, it says here, when ionizing or removing electrons, normally you're going to be removing the latest electrons that you would have added. So if you're talking about elements that are filling the s orbital, the 3s orbitals or the 4s orbitals, you'd be removing those first. Transition metals are a bit weird again, and if you are looking at a transition metal, you need to remove the electrons from the 4s orbital first, even though you feel like you've just been filling the 3d orbitals. Hopefully that makes sense. So if you have iron, which will have 4s2, 3d6, the last one you often write is 3d6, but if you take electrons away, you do not take them from the 3d orbitals. Instead, if you're taking away 2, for example, going from iron 2 plus, you've taken away 2 electrons, you take them away from the 4s orbital first. Now you can write the configuration 4s0 3d6, or you can just remove that 4s completely and write 3d6. Both are fine. And if we remove a further electron, so we first remove the 2 from the 4s orbital, if we remove any further ones, they will start coming from the 3d orbitals as expected, or as normal, as you can see in this row here. Now, once you can write those, now we have to worry about explaining the effect of absorbing or emitting radiation on the electron configuration of electrons in atoms or ions. Now, when an atom or an ion with electrons absorbs, it can absorb or emit light depending on what the electrons themselves are doing. So we'll start with absorption first. If you have an atom, the electrons are in energy levels, so they're quantized, they're in specific, not so much specific spots, but they have specific energies. You can absorb, or they can absorb light, as long as the light that they are being hit with corresponds to a transition from one energy level to another. So you can't, let's say you have an energy gap between 1 and 2, you cannot absorb energy that's equal to half of the gap between those two. It has to absorb the light corresponding to the full change between the two. Now that's not strictly true. If you have like a really high intensity light, you can sometimes have multi-photon, like you can absorb multiple photons at once, but that's far too complicated for what we're doing. Suffice it to say that atoms will absorb light, or atoms and ions will absorb light that correspond to transitions, or electronic transitions. So electrons will transit from one energy level, wherever they are, to another higher energy level when they absorb specific wavelengths of light, or specific colors of light. Now, correspondingly, if an electron is currently sitting at a higher than normal energy level, they can transition down from a high level to a low, and they will emit light at specific colors corresponding to those transitions. So if I were to show here, you've got this little electron here, it's sitting in energy level 2. It could absorb red light, so a small like a lower energy light to get to level 3, or it could absorb a bit more, be like a bluer color, and go up to a further level. Similarly, once that electron goes up to those levels, however it gets there, it could transition back down, and if it did do that, it would emit light at the same color as the color that it needed to absorb to get up to that point in the first place. Now, there are other ways of getting the electrons up to those levels, so you don't necessarily need to shine in the same color as you get back out, but again, more complicated than it's necessary. So we have, hydrogen is the most simple example because it only has one electron, and that is simple because once you have multiple, things just get a lot more complicated because the electrons start interacting with each other. If you really care, you can look up the 3-body problem as to why things are difficult. So these transitions that you see are the actual ones that we see for hydrogen. Hydrogen normally has one electron that would be sitting in the number 1 level by default, but if it's sitting in the second level because it's been excited by some other process, that electron from that position can go up from 2 to 3 or from 2 to 4, and those colors, the red light and cyan light, do correspond to the real transitions for hydrogen. Now, all of these transitions, for whichever elements we're looking at, they depend very heavily on the core charge of an atom. So the stuff that's going on right in the center. Now, because it depends so strongly on the number of protons in the nucleus, that means that if you have one element and its transitions, even if those and another element another ion happen to have the same number of electrons, it is still going to have unique transitions because the core charge, the number of positive charges in the nucleus, is unique to that element. Every element has this unique number of protons, therefore they will have a unique set of transitions, absorption or emission transitions. So I've got an example here. As I was saying, in other words, the 4s electrons in scandium and titanium, because of the different core charges in those two elements, they both have 4s electrons, but the core charges are different for those two, for scandium and titanium. Therefore, the 4s energy level will have a different energy. So the 4s doesn't refer to, so this doesn't tell us the energy of those electrons, it tells us the shape of the orbital that they're in. The energy that orbital will be at is different for every element because of that different proton number. So even if you're having electrons moving from the same orbital, let's say 4s up to, I probably should have done it more quickly so you can see, but 4s up to 4p or something. If you have transitions from there to there for both scandium and titanium, that will be a different color, a different amount of energy for each of them. Okay, now the next point, the wavelengths of radiation emitted and absorbed by an element are unique to that element. I've obviously just covered that before. Pretty much just to sum it up again, each element, either neutral or charged, will have a set of unique absorption and emission wavelengths which can be leveraged to identify the atomic composition of a substance. If you have a particular element in a substance and you can identify that element based on the colors or the emission spectrum. So if you heat it up, get the electrons nice and excited, then if you observe the light coming out of it, if you see specific set of emission lines, emission colors, then you can be confident that that particular element is in that sample. If you suspect that element, you can look for those colors. If you see them, it's there. If you don't see them, then it's not there. Yeah, again, all elements will be unique, have a unique set, which means you can always, if you are looking for one particular element, the fact that other elements are there will not impact that measurement. If you're looking at a particular color of light that only this element spits out and you don't see that light, the element's not there. If you do see that light, that element is there. No other species, no other chemical species being there, being present, will impact that. So I've got another example here. We have a continuous spectrum. So this here is a continuous spectrum where you have all of the colors that have been spat out. So the sunlight is like that because it's a very hot ball of gas. Now you can see there are these black lines that have been omitted, but the light, those are absorption lines. So essentially the sun will have tried to have emitted all of these colors, but there are some lines of light, some colors of that light missing, and these are very, very thin. I've exaggerated how thick they are, but those colors are missing because they've been absorbed between us and the sun's surface. Now, we scientists had to work this out, but it turned out that the hydrogen in the atmosphere of the sun is intercepting these colors that have been emitted from the hot plasma and absorbing them, which means they do not get to us. So as such, we have these lines which are all corresponding to the emission lines of hydrogen. Absorption lines of hydrogen, absorption and emission technically, but absorption lines of hydrogen that get removed from the sun's spectrum before they get to us. Now, just as an aside, here's that red, here's that cyan. These are those two transitions that we were talking about earlier, from level 2 to 3 and 2 to 4. Cool. And as I said, similarly, when you have atoms that are excited, because this is an absorption spectrum, similarly, if you have atoms that are excited, they can emit those same colors. Now, just as an aside, I also said you can absorb energy in a few ways. So light is one way. You'll absorb specific colors to move the lines up, but you can actually excite things with heat as well. So things like high temperatures. Now, you can identify. So you can qualitatively identify. So you can identify whether something is there or not. So an element is there or not in a particular sample using these techniques. So atomic absorption spectroscopy, you can just see if a sample is there, but you can also go one step further and identify how much of a sample is there. So if you see a particular color that is associated with this element, and you see it, that means that element is there. But how bright that light emitted, or how much light is absorbed, depending on the way you're doing it, will also tell you how much of a sample is there, or how much of that element is there, Now, we have something called the Beer-Lambert law, which just governs the absorption of light by substances. I keep saying substances, I mean elements. It can also be molecules as well, by the way, but we're only looking at atoms or ions in this course. So the absorbance, the overall absorbance of a sample, is a simple equation, three things, the product of three things. One is the concentration, that's how much of something there is. So obviously if you have more of a substance, more of an element, more of a molecule, then it's going to absorb more light. Now the path length. So the path length is an interesting one. I'm going to draw some stuff here. If you are sending some light through a box of this shape, and there's some particles in there that can absorb the light, if you were to send that same light through a longer path with the same concentration of stuff in it, it's just, it's passing through more of our, it has a greater chance of hitting our atoms or our ions or our molecules. Therefore, it's going to absorb more light. So the further the light travels, the more the light is going to interact with the material. Now, the last bit is the molar absorptivity. So that is a specific value that is unique to every different atom, ion, substance. It just governs how well that substance absorbs light. So some will just naturally absorb light more easily, or absorb a larger quantity, and that value, or this epsilon, will take that into account. Now, if you want to work out the concentration of a particular element or element in a sample, you use atomic absorption spectroscopy. Now, what you first have to do is you need to make sure that there's a light source inside that machine that corresponds to the element that you're looking for. If you don't have one, it just doesn't work, because you need to have the right colors that could be absorbed. So obviously if you have an element that you're trying to put some light in that it will absorb, but you don't have a source of that light, it doesn't really work. So the next thing you need to do is we don't really have a good way of dealing with this molar absorptivity. So what we can do instead is bypass that completely by doing a set of calibration curves. So these calibrations, if we have a particular element that we're looking for, we want to know what the concentration of that element is in an unknown sample. What you need to do is you need to put into your machine a bunch of samples of that element which the concentration is known, for which the concentration is known. So you will put into the machine a particular concentration that you know. So you make it up yourself from some standard chemicals, and you end up with an absorbance value, and then you'll mark that on your plot. You then need to do that across a range to give you these sets of these values, and then you will draw a line of best fit through them. Now they're not going to be perfect. As you can see here, I deliberately made it so that the lines, all these X's are not perfectly on that line. Regardless, you make a line of best fit that goes through them. So you can then put an unknown concentration of that particular element into your machine, and the absorbance will pop out. So it'll absorb a certain amount of that light, and let's say it corresponds to this value here. You then mark it off, you try and find out where it intercepts this best line of best fit, drop that down to the concentration, and that will give you our concentration of our unknown element, but our unknown concentration. Now so obviously, from this you can see that we need to make sure that the concentration of our calibrations are in the same range as our unknown, because if you had a whole bunch of things down here and then your concentration for your unknown was way up here, then you're going to have a lot of uncertainty in this line of best fit. So just a few points here that I've written down. Absorbance is directly proportional to concentration, as you can see from this this equation. So A is directly proportional to C. So if you just plot the absorbance versus the concentration, as long as you keep the molar absorptivity the same, which it will be for the same element, you keep the path length the same, which for the same machine or same apparatus, it should stay the same. You shouldn't be messing with that. You can bake those into the slope and just have a absorbance versus concentration graph where you can just simplify things. You have a linear trend line going through the origin, so because it's important that it goes through the origin here, because if your concentration is 0, your absorbance should be 0 as well. You shouldn't absorb any light at those wavelengths if you have none of that element. Now, as I said, I've illustrated to the left how you find the concentration of the unknown using its absorbance. You find out what it is, put it on the side here. If it was up here, you'd go across and then you'd drop down and find the concentration. One other point, not super relevant, but in the real world, if your concentration of your unknown is too high, it can actually the absorbance can go too high for the actual machine, and the machines are not considered to be accurate outside of them sort of mid-range. So what you would do is you would be very precise in your dilution of that unknown. So let's say it's too absorbent, you can dilute it by half to bring it down into this range. So let's say it was going to be way up here, and instead you dilute it by half and it ends up here. Then it's within our calibration range, and you can find out the concentration of that diluted sample, and you then do some simple calculation to get from your diluted sample up to your or back to your original. And I think we've covered that pretty well. So hopefully it helped. If anything was confusing, as always, just let me know in person.